Ayubowan, everyone. So glad you could join me today on our Study Hub Sri Lanka channel. Right, today we're kicking off a really important chapter for your AL chemistry, atomic structure. Think of it like this. We're about to go on an incredible journey deep inside the atom to figure out what it's all about. Ready to get started? All right, so let's start with a really big question. A simple one, but a deep one. Just look around you. The book in front of you, the pen in your hand, even the air that you're breathing. What is all of it really made of? I mean, if you could just keep breaking it down into smaller and smaller and even smaller pieces, what's the last thing you'd be left with? You know, this is the very question that got scientists thinking for hundreds and hundreds of years. Now, you might be thinking this idea of a tiny fundamental particle is a modern thing, but it's not. Way back, ancient Greek philosophers, guys like Democritus, they had this idea. They imagined a particle so small you couldn't possibly cut it any further. And they gave it a name, atomos, which literally means uncuttable. Pretty cool, right? But here's the thing. That was philosophy, just an idea. It wasn't based on actual experiments. So for our journey, we're going to jump ahead to where the science really begins. And that's where we meet John Dalton, an English school teacher back in 1808. He came up with the first proper scientific theory of the atom, and it was brilliant. He laid out a few key ideas. 1, everything is made of these tiny little particles called atoms, and you can't divide them. 2, if you take an element, say gold, all the gold atoms are exactly the same. 3, in a chemical reaction, you're not creating or destroying atoms, you're just shuffling them around. And 4, compounds, like water, are just atoms of different elements stuck together in simple, fixed ratios. I mean, this was a huge leap for chemistry.
So this is him, John Dalton. And based on his theory, what did he think an atom looked like? Well, pretty simple, really. Just a tiny, solid, hard ball. Kinda like a miniature golf ball. No protons, no electrons, nothing inside. Just one solid piece. For him, that was it. The smallest possible building block. But was that the whole story? As we're about to see, science never stops asking questions, and new discoveries were just around the corner, ready to challenge this golf ball idea.
Right. So scientists didn't just accept Dalton's model. They tested it, and their experiments started showing something surprising. That indivisible golf ball, turns out it did have smaller parts inside, and the very first of these tiny little pieces they found was something called the electron. And let me tell you, this discovery, it changed everything. And this is the piece of equipment that blew the whole thing wide open. It's called a cathode ray tube. Basically, it's a glass tube with most of the air sucked out to create a near vacuum. You've got a negative plate at one end, the cathode, and a positive plate at the other, the anode. Now, when you connect it to a super high voltage power supply, something incredible happens. A strange beam, a glow, shoots from the negative end to the positive end. They didn't know what it was, so they just called them cathode rays. Okay, so scientists were fascinated by these mysterious rays and started doing all sorts of experiments on them. And they figured out 3 really important things. First, these rays travel in perfectly straight lines. Second, they weren't just light, they were actual particles with mass and energy. And third, these particles had a negative charge. But how on earth did they know all that? Let's break down the proof for each of these points. First up, how did they prove the rays travel in straight lines? Well, it was actually pretty clever and simple. You know how sunlight casts a really sharp shadow? They did the same thing. They put a small metal object, shaped like a cross, right in the path of the beam. And guess what? A perfectly crisp, sharp shadow of the cross appeared at the other end of the tube. That can only happen if the rays are traveling in a dead straight line, right? Okay, this next part is really cool. How did they know it was made of actual particles and not just some kind of light? They put a tiny little paddle wheel inside the tube, a really light one, and when they turned on the cathode rays, the wheel started to spin. Now think about it. For something to push a wheel and make it turn, it has to have mass, it has to have energy. This was absolute proof that they were dealing with a stream of actual tiny particles. So the last piece of the puzzle was figuring out if these particles had an electrical charge. So what they did was, they put 2 extra plates outside the tube, one positive and one negative. And when they turned it on, the beam of rays bent. It curved towards the positive plate. And what do we know about charges? Opposites attract. So this was the final confirmation. These particles were negatively charged, and it was J.J. Thomson who did a lot of this work and finally gave them their name, electrons. Okay, let's pause and think for a second. We know that atoms, in general, are neutral. They don't have an overall charge. But wait.
We just found out they have these negative little things called electrons inside them. So how can that be? Well, it's simple logic, right? If there's negative stuff inside, there has to be some positive stuff in there too to cancel it out and make the whole thing neutral. So the search began for the atom's positive particle.
And they found it by again playing around with a cathode ray tube. This time they used a cathode that had little holes drilled in it. And when they ran the experiment, they noticed another set of rays, this time going in the opposite direction. They were streaming away from the positive anode and passing through the holes, or canals, in the cathode. And when they tested these rays, yep, they were positively charged. Eventually, this fundamental positive particle was given its name, the proton. So by now, the picture of the atom is getting a little clearer. We've got positive protons and negative electrons. But how are they arranged? Where are they inside the atom? The most popular idea at the time was called the plum pudding model. Just imagine a ball of positive pudding with negative electrons scattered around inside it, like raisins or plums. It made sense, but a new experiment was about to come along and just blow that whole idea out of the water. And this is it. The famous, legendary gold foil experiment led by Ernest Rutherford. The setup was actually genius in its simplicity. You have a source that fires out these tiny, very fast, positively charged things called alpha particles, kind of like a tiny machine gun. And the target? An unbelievably thin sheet of gold foil. I mean, just a few thousand atoms thick. Then, all around it, he placed a special screen that would make a tiny flash of light every time an alpha particle hit it.
Now, based on that plum pudding model, what did Rutherford expect to happen? He thought all those alpha particles would just zip straight through the gold foil like bullets through a cloud. And his first observation was, yeah, most of them did go straight through. But then came the surprises. A few of them were deflected, pushed off course a little bit. And then the absolute shocker. A very, very tiny number, we're talking like 1 in 20,000, actually bounced almost straight back. Rutherford himself said it was like firing a cannonball at a piece of tissue paper and having it come back and hit you. It just didn't make any sense. So how could he explain this bizarre result? The only possible explanation for a positive alpha particle bouncing straight back was that it must have hit something incredibly small, super dense, and also positively charged. And this led to him to a revolutionary new model of the atom, the nuclear model. His idea was this. The atom is actually mostly empty space. That's why most particles pass through. But right in the middle, there's this tiny, dense positive center called the nucleus, where all the positive charge and almost all the mass is packed. Okay, so with this new nuclear model, we can finally start putting some numbers on these atoms. Think of these numbers like an atom's personal ID card. They tell us exactly which element we're looking at and give us an idea of its mass.
Right, the most important number of all is the atomic number. We use the letter Z for it. And it's super simple. It's just the number of protons in the nucleus. That's it. But this number is everything. It's what defines an element. For example, any atom in the entire universe with 6 protons is a carbon atom, period. If it had 7 protons, it's not carbon anymore, it's nitrogen. The atomic number is literally the atom's identity.
The next number you need to know is the mass number, and we use the letter A for that. Now, we've learned that protons are not alone in that tiny nucleus. There's another particle in there called the neutron. Neutrons have no charge, but they have about the same mass as a proton. So the mass number is just the total number of protons plus the total number of neutrons in the nucleus. Simple as that. And we have a really neat way to write all this information down using the atomic symbol. Let's look at carbon. You see the big C and then 2 numbers. The number at the bottom is Z, the atomic number. So for carbon, that's 6, which tells us it has 6 protons. The number at the top is A, the mass number, which is 12. So, quick question for you. How many neutrons does it have? Well, it's just the mass number minus the atomic number. So 12 minus 6 gives us 6 neutrons. See? Really easy.
Now, this leads to a really interesting question. Can you have 2 atoms of the same element, but with different masses? And the answer is yes, absolutely. We call them isotopes. Isotopes are atoms that have the exact same number of protons, so they're the same element, but they have a different number of neutrons. A classic example is carbon. Most carbon is carbon-12, with 6 protons and 6 neutrons. But there's also carbon-14, which still has 6 protons, but it has 8 neutrons. So it's still carbon, just a little bit heavier. All right, up until now, we've been talking about neutral atoms, where the number of positive protons is exactly balanced by the number of negative electrons. But what if that balance gets disturbed? What happens when an atom either loses an electron or maybe gains one? Well, it's no longer neutral. It becomes a charged particle, and we have a special name for that, an ion.
Let's look at these two examples. On the left, we've got a sodium atom. Normally, it has 11 protons and 11 electrons, so it's perfectly neutral. But if it loses one of those electrons, what happens? It still has its 11 positive protons, but now it only has 10 negative electrons, so it has an overall positive charge of +1. We call a positive ion a cation. Now look at chlorine on the right. It has 17 protons and 17 electrons. But what if it gains an extra electron? Well, now it has 18 electrons. So with 17 protons and 18 electrons, it has an overall negative charge of -1. And we call a negative ion an anion. And that's a wrap on our first look inside the atom. Wow, we've covered a lot of ground today, haven't we? From Dalton's simple little golf ball idea all the way to Rutherford's amazing discovery of the nucleus with all its protons and neutrons. I really hope this lesson has helped you understand these key concepts. Thank you so much for tuning in. Now, to make sure you catch part 2 of this lesson, please do me a favor and subscribe to our Study Hub Sri Lanka channel. And don't forget to click that little bell icon. That way, we'll get a notification the moment the next video is up. Until then, study hard, and I'll see you for the next science lesson. Take care, everyone.